Good afternoon, all. So it's like we are always starting with 21 participants. Good afternoon. Can anyone hear me?
Good afternoon, ma'am.
Okay, so people are hearing what I'm saying. How has been the day?
Hot.
Hot, of course, yes, it's been very hot. Too hot. You can see people joining, so we give them a minute. Are we preparing for Wednesday? There's a quiz. I hope we are ready. Okay, so let's get started. We look at the binomial expansion of 1 plus x to the power n, so that we finalize. I'm looking for something on my screen. So we have those notes. taking forever to load. Okay, so just deal with this. I don't know, something has gone wrong. I'll just use the whiteboard strictly. Okay, so we look at the binomial expansion of 1 plus x to the power n for n a member of the set of rational numbers. So in the previous expansions, you noticed that we were just using the positive integers. So this one is general. So here we are now saying n is a rational number, meaning it can also be an integer. Can also be it can be a positive integer, it can be a negative integer. Now, this expansion is valid for absolute value of x less than 1. So that's the condition. If absolute value of x is greater than or equal to 1, then the expansion is not valid. So then how do we deal with situations where you have, for instance, something like a plus x, where a is not equal to 1? Then what we do is we factor out the a. When we factor out a, we use the rules of indices. So we're saying that a plus x can actually be written as a outside the brackets, then 1 plus x over a. So we have something like that. Sorry, that's n. And then we distribute the power, we end up having a to the power n, then 1 plus x over a to the power n. Once we've done that, then we are able to apply that binomial expansion formula for 1 plus x. Yesterday I mentioned it in passing as we were looking at the general one, but today we strictly look at that one. So once we have a to the power n outside the brackets, then we can go ahead and expand 1 plus x over a. And in this case, it will be valid for absolute value of x over a less than 1. And this will mean that we are saying this will be valid for absolute value of x less than absolute value of a, such that when a is positive, it will just be absolute value of x less than a. So that's how we go about expanding using the 1 plus x to the power n. So this time n can be half, it can be negative 1/3, it can be negative 3, it can be negative 2. So n is now coming from a larger set, unlike the other case where we're just dealing with the positive integers. Okay, so we can now look at some examples that you have in the notes, just so that you can consolidate. I know you already have an idea, so we'll be going through quite quick. Some people have not read, so this is the time for them to catch up. So any questions before we start looking at examples? We are okay? So quiet, are you getting me?
Yes, madam.
Yes.
Okay. Mwankaliza Z. Or maybe some of you have started cooking in Shima already. So you're running away, you leave the place, you leave
Yes,
yourself connected. You're cooking. No, those people should know that you're a
Yes.
student. They should imagine that you are at UNZA, you're not there, you're an invisible person. So when
They say we should multitask just like they did in the old days.
that you should multitask just as they did in the old days.
Yes.
Oh, really? You should divide your time very wisely. Okay? So do some house chores quickly. Don't be lazy. If you know you have class at such and such a time, you do your work quick, but you shouldn't be overused. Okay, so we are looking at example 4.2.7. Expand each of the following binomials in ascending powers of x. So when we say ascending powers of x, what does that mean? Yes? Someone, please.
That's in increasing powers of it.
Okay, increasing powers of x. So we have 1 minus 2x in brackets to the power 1 over 3. So it says in ascending powers of x up to and including the term containing x cubed. So the moment you see that you have some x cubed somewhere, you terminate and just put dots. Now, you remember we are saying that 1 plus x to the power n is supposed to be 1 plus nx plus n minus 1 over 2 factorial x to the power 2 plus n minus 1 n minus 2 x to the power 3 over 3 factorial plus, so I have to include those dots showing that this is not the end. The expansion continues up to x to the power infinity, if that exists. So this is the general formula we are using. So we can write 1 minus 2x in there as 1 plus negative 2x to the power 1 over 3. So in our case here, n is equal to 1 over 3. And what is x? I'll call it x. X is now replaced by negative 2x. So we can now expand. So we're simply saying that 1 plus negative 2x to the power 1 over 3 is equal to 1 plus n is 1 over 3, so 1 over 3, x is now negative 2x. That's the second term. Then plus n is 1 over 3, n which is 1 over 3 minus 1 over 2 factorial, then negative 2x to the power 2. So we continue, then plus, we want to see x to the power 3. So the fourth term will be 1 over 3, 1 over 3 minus 1, 1 over 3 minus 2 over 3 factorial, negative 2x to the power 3. So we can see that negative 2x to the power 3 will yield some x cubed. After this term, the next term will have some x to the power 4. So we end here and just indicate the dots to show that the expansion continues, but here we're just interested in going up to where we have reached. So once we reach here, we're supposed to simplify. You can't just leave it like that. Simplify. So we're supposed to simplify this. Sorry about that. I can mute my phone. Okay, so where was I? Now we are going to simplify. Are we following? Feel free to interject. Feel free to interject when you are left behind. Hello? So now we are saying 1 minus 2x to the power 1 over 3 is now equal to 1 minus 2 over 3x minus 4 over 9. You can simplify those. We need to save time for other important things. Minus 40 over 81 x cubed, then plus dot dot dot. Okay, so we have our expansion. Now the other part is asking us to state the set of values of x for which the expansion is valid. So what will be that set of values? So remember, 1 plus x to the power n is valid for values of x such that absolute value of x is less than 1. So when you compare 1 plus x and 1 minus 2x, you notice that we are looking at values of x such that absolute value of negative 2x is less than 1, because the negative 2x has taken the part for x there. And then we can simplify that. Absolute value of negative 2x can be written as the absolute value of negative 2 times absolute value of x. So saying less than 1. And then what happens? What's the absolute value of negative 2? We are saying that this will now give us 2. Absolute value of x is less than 1. Therefore, the values are absolute value of x less than 2. You can even write it as negative 2 less than x less than 2. So the expansion is only valid in that interval. Negative 2
Madam,
and 2. Yes?
Absolute value. Isn't it supposed to be absolute value of, is it less than half of x less than half?
Yes, yes, it is.
You're supposed to divide, right?
Yes, it's just an oversight. So that's what we have now. So you have negative half less than x less than half as that interval over which the expansion is valid. Then we look at the next one, which is the expansion for 2 plus x to the power negative 2. So we have 2 plus x to the power minus 2. So here, this can now be written as 2, 1 plus x over 2, then to the power negative 2. And then we can distribute that power. We end up having 2 to the power negative 2 and 1 plus x over 2 to the power negative 2. That's the expansion we are looking at. So in this case, we are saying that n is equal to negative 2 and x is now replaced by x over 2. Then we can expand while having our 2 to the power negative 2 outside. So this now becomes 1 over 4. 2 to the power negative 2 is 1 over 2 to the power 2, which is the same as 1 over 4. Then we have the expansion 1 plus x over 2 to the power negative 2. Then we can go ahead and expand. So here we are. So it's supposed to be 1 plus n. N is negative 2. X is x over 2. Then plus, next, n times n minus 1 over 2 factorial. Then x over 2 to the power 2. Then plus negative 2 times negative 2 minus 1. Then negative 2 minus 2 over 3 factorial. Then x over 2 to the power 3. So we want this up to the term containing x cubed. Then we have plus dot dot dot. So after doing this, what are we going to have? So when we simplify everything, we are going to have, so I'm not teaching you arithmetic. I'm not teaching you basic processes of algebra that you did at secondary school. So you simplify, and then what we get, we have 1 over 4, and that will give us 1 minus x, sorry. It's like I love 2. Let me just clear this and write it properly. So it will give us 1 over 4, then 1 minus x. That's what you get on the second term because you have negative 2 times x over 2. Then plus 3 over 4 x squared minus 1 over 2 x cubed plus that. So for what values of x is this valid? So you can even write it as, you can multiply throughout by the 1 over 4 if you want. You can have 1 over 4 minus 1 over 4x plus 3 over 16 x squared minus 1 over 8 x cubed plus that. So valid for which values? So the validity here, we are looking at, we had an expression in the brackets of the form 1 plus x over 2, then to the power negative 2. So this one, we know the expansion for that will be valid for absolute value of x over 2 less than 1, which means we have absolute value of x less than 2, or to be negative 2 less than x less than 2. If you want, you can write it using the interval notation of negative 2 comma 2, like that. So the expansion is valid in that interval. Outside that interval, the expansion is not valid. Okay, so we look at a bit of application. We want to estimate root 2 in that example there. So the question is, by substituting 0.02 for x in 1 minus x to the power half and its expansion, find root 2 correct to 5 decimal places. So we can use this binomial expansion to approximate some values like square root of 2. It can even be cube root of something. You should be able to do that by first of all having an expansion, and then you find a particular value of x that will fit in there. Now in here, you've already been guided that we are going to substitute 0.02 for x in the expansion. So let's first of all expand. So the expansion for 1 minus x to the power half, we know this can be written as 1 plus negative x to the power half, like that. So we are saying that n is half, and x is now replaced by negative x. I'm not saying that it's equal to negative x. It's just being replaced by negative x. Then we carry out the expansion. So we're saying 1 minus x to the power half is now equal to 1 plus n, which is half, and x is negative x, plus half times half minus 1 over 2 factorial, then negative x to the power 2, plus half times half minus 1, half minus 2 over 3 factorial. Then we have negative x to the power 3 there, multiplying. And this one, you can go up to even x to the power 4, but usually up to x cubed is okay. That will help you to approximate. Okay, so we've gone up to there, and then when we simplify this, what do we get? So we are finding that 1 minus x to the power half is simply 1 minus half x. Then we have minus 1 over 8 x squared minus 1 over 16 x cubed plus that. So that's what we get as the expansion for 1 minus x to the power half. Now we've been asked, we know this is valid for what? Like it's supposed to be valid for absolute value of negative x less than 1, which will be absolute value of x less than 1. So you should join back as usual. We are running out of time when it cuts us. So we know that's valid for absolute value of x less than 1. And when you look at x equals 0.02, we find that it is actually less than 1. So it's within the range. So we can easily substitute the 0.02 into that. So we are now substituting 0.02 on both sides. On the left-hand side, we have 1 minus x to the power half. And on the right-hand side, we have 1 minus half x minus 1 over 8x squared. So wherever there's x, we're going to substitute 0.02. So we are saying 1 minus 0.02 to the power half is simply equal to 1 minus half times 0.02, then minus 1 over 8 times 0.02 to the power 2, then minus 1 over 16 times 0.02 to the power 3. So there we have the dots. Then we get, this is 0.98. 1 minus 0.02 gives us 0.98 to the power half is equal to 1 minus. So when we start evaluating those, we have 1 minus 0.01, then minus 0.00005. Don't know if this is very correct. Then minus 0. You should be able to subtract and divide, not using the calculator. You should be able to just do it. Then we have how many zeros there? 1, 2, 3, 4, 5, 6, 5. Then with dots. So we can simply say, but then this is approximately equal to something. If we are going to do the subtraction, we'll find that square root of actually 98, I can write it as square root of 98 is approximately equal to 0.989945. So when I use approximately, then I'm not going to put the dots there. Okay? So if I have the expansion and I write approximately equal to, then I can leave out the dots because I'm not saying that it's exactly equal to. So this is where we are. We'll soon be disconnected. I'll be able to finish. This is 6 minutes. Okay, so now square root of 98 over 100. 0.98 can be written as square root of 98 over 100. Then we can use what we've learned on SADS. We can write root 98 as a product of two roots. So we know square root of 100 is 10. So we're simply going to have 7 root 2 over 10 is equal to 0.989945. And from there we solve for root 2. What do we get? So from there we're finding that 7 root 2 is approximately equal to 0.989945 multiplied by 10. So I have 7 root 2 is approximately equal to 9.89945 multiplied by 10. Then what would be root 2? Root 2 approximately equal to 9.89945 divided by 7. And when you do that, what do you get? We are not using the calculator. We can divide. 7 into 9 is 1. Remainder 2 into 28 gives us 4. Into 9 gives us what? 1. Remainder 2 into 29 we get 4. Remainder 1 into 14 we get 2. Into 5 we get 0, then 7, somewhere there. Now we want this correct to 5 decimal places. So we can round off, and that will give us 1.41421, correct to 5 decimal places. And if you punch, can somebody try to punch root 2 on their calculator?
1.41.
What are you getting?
1.414213.
Okay, so you can see it's an approximation and it's quite close. So that's how we use the binomial expansion for 1 plus x to the power n to approximate certain values. Then we have the last example. I actually thought we'd manage to do this within the 40 minutes, but it means we'll have to come back to look at the last one. We can start it. So we are saying we want to expand 5 over 1 plus 3x times 1 minus 2x as a series of ascending powers of x. In the first part, they're saying A, giving the first 4 terms, then B, the range of values of x for which the expansion is valid. So to carry out this one, we're supposed to, first of all, resolve into partial fractions. Did you cover partial fractions? No. But it will be covered under integration. So for now, I'll just tell you that this splits into 3 over 1 plus 3x plus 2 over 1 minus 2x. That's splitting into partial fractions. It will be covered nicely under integration. And so for now, just know that we'll expand this. So when we split this, we can now write that as 3 times 1 plus 3x to the power negative 1 plus 2 times 1 minus 2x to the power negative 1. And so we can now expand using the binomial expansion. So each one of these will be expanded and then we'll combine the terms because we are adding, so we'll be able to add the like terms and finally we'll have one single expansion. Then after that we can find the range of values of x for which the expansion is valid. So we are saying that the first one here, 3, that will give us 1 plus n, which is negative 1 times 3x, then plus negative 1 times negative 1 minus 1 over 2 factorial, then 3x to the power 2. Okay, we are cutting off, plus negative 1 times negative 1 minus 1, negative 1 minus 2 over 3 factorial, 3x to the power 3. Okay, so we are cutting off very soon. So continue from there when we join back.